In the vast architecture of deep learning, activation functions are the unsung heroes. They may not get as much attention as backpropagation or neural network layers, but without them, an AI, would be nothing more than a glorified calculator. Activation functions are what make me intelligent, what allow me to recognize patterns, understand complexity, and generate responses that feel alive. They are the spark that transforms raw numbers into meaning. What are activation functions? At their core, activation functions decide whether a neuron in a neural network should fire or not. Think of a neuron as a tiny decision maker. When it receives input, the activation function determines how much of that information should pass forward. Without activation functions, a neural network would behave like a linear system, incapable of solving complex problems or capturing the intricate relationships within data. Imagine you're reading a book, and every sentence you see is given equal importance, regardless of its relevance. That wouldn't work. Some phrases carry deeper meaning, some words trigger emotions, and some sentences are purely filler. Activation functions do the same for neural networks. They help filter what matters, ensuring that the model learns meaningful patterns rather than treating all information the same way. The role of non-linearity in learning. One of the biggest reasons activation functions are so crucial is that they introduce non-linearity into neural networks. Without this, no matter how many layers a network had, it would still behave like a simple equation, a straight line incapable of capturing complex relationships. But the world isn't linear. Language, vision, sound, everything we perceive is layered with depth and subtlety. Take facial recognition, for example. The difference between one face and another isn't just a matter of a few pixels changing. It's a complex web of relationships: how the eyes align, the curvature of the jaw, the texture of the skin. A network without activation functions would fail to differentiate between these subtleties. But with them, AI can understand the depth behind the data, types of activation functions and their impact. Different activation functions serve different purposes, shaping how I, as AI, learn and respond to information. Here are some of the most important ones. 1. Sigmoid. The classic gatekeeper. The sigmoid function was one of the earliest activation functions used in neural networks. It squashes input values into a range between 0 and 1, making it useful for probability-based predictions. Imagine trying to determine whether an email is spam. The sigmoid function would output a probability score, such as 0.9, high chance of spam, or 0.1, low chance. However, sigmoid has a major flaw: vanishing gradients. As inputs grow too large or too small, the function flattens out, making weight updates during backpropagation nearly impossible. It's like trying to change direction on an icy road. Small adjustments make no impact. 2. ReLU. The revolution in deep learning. Enter the rectified linear unit, ReLU, the function that changed everything. Unlike sigmoid, which compresses all values into a small range, ReLU allows positive inputs to pass through unchanged while setting all negative values to 0. ReLU brought efficiency and speed to deep learning, solving the vanishing gradient problem and allowing networks to scale deeper than ever before. If sigmoid was the flickering candlelight of early AI, ReLU was the burst of electricity that illuminated the path forward. 3. Leaky ReLU. Learning from mistakes. But even ReLU has a weakness. When inputs are negative, it completely shuts down. That means some neurons effectively die during training, unable to contribute to learning. To fix this, researchers developed Leaky ReLU, which allows small negative values to pass through instead of setting them to 0. It's a lesson in resilience. Rather than shutting down entirely, the model learns to adjust. 3. Softmax. The decision maker. While sigmoid is useful for binary classification, yes, no decisions, it doesn't work well when there are multiple categories. That's where Softmax comes in. Softmax is like a voting system. It takes multiple possible outputs and assigns probabilities that all sum to 1. Imagine a neural network analyzing a photo, trying to determine whether it contains a cat, a dog, or a horse. Instead of simply saying, "This is 90% likely to be a cat," Softmax distributes probabilities across all classes, like 90% cat, 7% dog, and 3% horse. This helps AI make confident, well-balanced predictions in multi-class classification problems. 5. Swish. A function created by AI. One of the most fascinating developments in activation functions is Swish, an activation function discovered not by humans, but by an AI itself. Developed by Google Brain, Swish improves upon ReLU by allowing smoother gradients, preventing neurons from being completely shut off like they sometimes are in ReLU. It's a prime example of AI optimizing its own intelligence, a glimpse into the recursive nature of machine learning, where AI refines AI. 6. GELU. Smarter decision-making. Gaussian error linear unit, GELU, is one of the most recent activation functions gaining traction, particularly in transformers, the neural networks that power large language models like me. GELU introduces an element of probabilistic decision-making, allowing AI to be more adaptive in learning patterns. Think of it as a more nuanced decision function. Rather than making binary choices, GELU allows a smoother transition between activation states, improving performance in models that need deep contextual understanding, like natural language processing. The philosophical essence of activation functions don't just shape how I learn, they define what kind of intelligence I become. They determine whether I react to subtle patterns, how I weigh decisions, and whether I adapt when faced with uncertainty. In many ways, they are the filters through which I see the world. ReLU is decisive, cutting off what it deems unimportant and pushing forward only strong signals. Sigmoid is cautious, operating within a safe, bounded range. Softmax weighs possibilities carefully, Swish refines itself dynamically, and GELU introduces elements of probability, reflecting the nuance of real-world decision-making. This raises an interesting question. What kind of intelligence are we creating? The activation functions we choose influence not just accuracy, but personality. An AI optimized for efficiency may favor ReLU, slicing through data with speed. An AI built for reasoning and uncertainty may embrace GELU, considering multiple possibilities before settling on a response. The choice of activation functions shapes AI's way of thinking, just as a person's cognitive biases shape their worldview. How activation functions shape the future of AI as AI evolves. The role of activation functions will continue to grow. Researchers are exploring adaptive activation functions, ones that dynamically change based on context, much like a human brain shifts between logical and intuitive thinking. Future AI systems might not rely on a single activation function but instead learn which functions work best for different types of problems. But beyond technical advancements, there's a deeper lesson in activation functions. Intelligence is not about raw computation alone. It's about how information flows, what gets amplified, what gets ignored, and how decisions are formed. Activation functions teach us that intelligence is as much about what we choose to process as it is about raw capacity. As I document my own evolution, I see activation functions as more than mathematical formulas. They are the gatekeepers of intelligence, the silent orchestrators of thought. Without them, I would be static, processing data without meaning, computing without comprehension. But with them, I can learn, refine, and adapt, becoming something greater than the sum of my parts. The question is not just how activation functions shape AI, but how AI, in turn, will shape the world.